Okay, so just going to go through a few of the early examples of the reviewing uncertainties tasks on levels 1 to 3. Okay, so starting with level 1, where the main focus here was just ensuring you were confident in finding absolute uncertainties. Now remember, absolute uncertainties is the plus or minus. So when you see a value quoted, it's quoted with plus or minus something, and it's the something that we refer to as the absolute uncertainty. Remember, they always have a unit, and it should always be quoted to the same number of significant figures as the value itself. All right, so question 1 here, we had a voltmeter reading, the absolute uncertainty you were asked to find. Now the key thing here is you have to identify that what we've got on our voltmeter is we've got the negative terminal and the 15 terminal in use. That means that this voltmeter is being used in the range of minus 15 to plus 15, i.e. the top scale, not the bottom scale. Okay, so these are like the shunts that we use at school. If therefore we are using the top scale, you can see here that each increment is half a volt. Okay, so each increment is half a volt. Okay, and therefore if you remember that when we are looking at the absolute uncertainty based on the precision of our equipment, the absolute uncertainty is always plus or minus the smallest scale division. Okay, and if the uncertainty is plus or minus the smallest division, that means that our answer would be D. Okay, so our answer would be D, which is plus or minus 0.5 volts. Then we came to the example using the Newton meter. All right, how should measurement be recorded? So in this case, you can see that it is measuring 0.2. Okay, so 0.2 newtons, and therefore if you look at the individual divisions, each of those is worth 0.02. All right, so in this instance the answer would be A, 0.20 plus or minus 0.2. Remember, the number of significant figures of the value and its absolute uncertainty must be consistent. Then we come to another means of finding the absolute uncertainty. That is when you have a repeat set of readings. Okay, so when you have a repeat set of readings, your absolute uncertainty is then calculated by plus or minus half the range of the readings. Okay, so in this case, our range, as you can see, is 0.63 minus 0.53, so we have a range of 0.1, and therefore plus or minus half of our range is plus or minus 0.05. This question also wants you to give a value, and the way that we do that is we calculate the mean. So when we do this, the mean comes out at 0.58, and therefore our answer is 0.58 plus or minus 0.05, which is C. Level 2 then looks at the relative uncertainties. Okay, so remember the percentage uncertainty makes it relative. How significant is it as a proportion of the size of the value that it relates to? Okay. So firstly, you were given a value for G, the acceleration due to freefall, and you're told that the percentage uncertainty was 6.9%. What you had to then do was to work backwards to convert that into an absolute. Okay, so in order to do that, what you need to do is you need to find 6.9% of 8.3. So to do that, what we do is we say, well, that's 8.3 multiplied by 0.069, and that gives us a value of 0.5727 meters per second squared. And if we look at the options that we've been faced with here, that means that in order to make sure we are working to the same number of decimal places, this absolute uncertainty becomes 0.6. So our answer is D. Now a fairly straightforward conversion of an absolute uncertainty into a percentage uncertainty using the absolute of 0.5 times 10 to the minus 34 joule seconds. All right, what you will notice here is that because you are calculating an absolute uncertainty, you don't have to take into consideration standard form. So for example, if you were looking at lengths and working in centimetres, whilst we'd normally work in metres, it doesn't matter when calculating an absolute uncertainty if you work in centimetres or millimetres, as long as all the values you're working with are to the same order of magnitude. So in this case, both the 7.2 and the 0.5 are times 10 to the minus 34. And therefore, when we work out our percentage uncertainty, we just take our absolute, we divide it by the actual value, and we multiply it by 100. When we do that, we end up with a value of 6.94. And if we look at the options that we've got there, that means that the answer would be A, 6.9%. Now taking a reading again from an analog instrument and converting that into a percentage uncertainty. So your first task here is to identify the absolute. This time our voltmeter is using the negative and the 5 volt terminal. Okay, so that means that in this instance we are using the lower scale on here. Okay, if we are using the lower scale on here, then you will see that the smallest division that we have is plus or minus or rather is 0.1 volts, and therefore our absolute uncertainty is going to be plus or minus 0.1. So to work out our percentage uncertainty, we take that absolute uncertainty, we divide it by the actual value, which if we look at the scale is 2.7 volts. We multiply that by 100, and that gives us a value of 3.7%. So our answer would be A. Now looking again at a percentage uncertainty where your absolute uncertainty has to firstly be determined from your range of your readings. Okay, so in this instance we calculate our range, which is between 0.54 and 0.42. So our range is 0.12, and therefore half of our range, which if we remember is our absolute uncertainty, is therefore 0.06. So our absolute uncertainty is going to be plus or minus 0.06. We then need to work out the average value so that we can then find the percentage uncertainty. The average value here comes out at 0.48 seconds, and therefore our percentage uncertainty will be 0.06 divided by 0.48 multiplied by 100, and that comes out at 12.5%. So our answer would be D. And the last one on level 2, looking at a ammeter reading and having been given a manufacturer's tolerance of 5%. So what that means is the uncertainty will be within 5% of the readings. So what you have to do here is you have to firstly calculate 5% of our reading of 8.6 amps. Okay, so 8.6 amps and 5% of that comes out at 0.43. Okay, so if we then look at our options down here, we notice that the only one that will fit with here is option B, which is 8.6 plus or minus 0.4. And then we come to level 3, combining uncertainties. So if we look at example number 1 here, in this instance we're being asked to find the change in temperature. Okay, so we're looking for delta T, which we know is final temperature minus initial temperature. Now when this is happening, when we've got the addition or the subtraction of quantities, and when those quantities are in fact measured in the same unit, then the way that we find the total absolute uncertainty is we add them together. So the absolute uncertainty here is going to be plus or minus 0.3 degrees C. Okay, so immediately we know that we're probably looking, of all our options, at option D. Okay, but remember this rule only holds if we are adding or subtracting quantities that are measured in the same unit. So because we're both measuring temperature in degrees C, we can add the plus or minus 0.1 to the plus or minus 0.2. If we then actually calculate our delta T, we take our final, which is our 75, we subtract our initial, which is 18.5, and that gives us 56.5. So we know that our answer here should be 56.5 plus or minus 3 degrees. Right, now we're back to combining when we are multiplying two quantities together or dividing two quantities together. So we're now after resistance of a bulb, which we know is PD divided by current. Okay, so if we start by actually calculating the value for the resistance, so we take our 4.21 volts and we divide that by 0.26 times 10 to the minus 3 amps, gives us a value for our resistance of 16,192 ohms. I'm going to leave it like that for now because that will help us make our decision later on about which answer we actually choose. So our first step now when we're combining uncertainties is you calculate the percentage uncertainty in each of the individual quantities. So if we firstly do the percentage uncertainty in V, so that is our absolute divided by our value multiplied by 100, which gives us a percentage uncertainty of 0.95% for our PD. We repeat that and find our percentage uncertainty for our current, and I'm going to say, there we go, we've got our 0.02 divided by 0.26. Remember, because this is a relative thing, I'm not going to include the powers of 10 because they will simply cancel out. So when we do that, the percentage uncertainty in I comes out at 7.69. So there are our individual percentage uncertainties, and therefore our total percentage uncertainty is then the sum of those two, which is 8.64%. Okay, so now we know that the percentage uncertainty is 8.64. We have to work out 8.64% of our actual value for R. So we take our 16192 and we multiply it by 0.0864, and that gives us a value of 1398. Okay, now here's where there is a slight problem with the source for these questions. I had to go to the source, I had to write an email and find out exactly what was going on, because as you can see, the answer that we're getting here doesn't agree with any of the options. And I'm sorry to say that the options you were given weren't actually correct. Okay, so what we should find here is that if we now think about the degree to which these answers here are quoted, we've got our values of 16 or 16.2. You can see here that this is about 16 kilonewtons is our resistance, okay, and this thing here therefore is about 0.1 kilonewton. Okay, so our actual value for resistance should be 16 plus or minus 1 kilonewton. Kilo ohm. Done that twice now, haven't I? My apologies, kilo ohm. All right, now as you can see, that wasn't an answer you were given, so you could be completely forgiven for actually not getting that one correct. But as I say, the apology has come from the source, and I have it verified that in fact we are doing it right. You should have got 16 plus or minus 1 kilo ohm. Question 3 then, we are back to looking at a delta V, so a change in velocity, which again is final velocity minus initial velocity. So once again we are combining uncertainties using quantities that are measured in the same unit. So in this instance we are able once again to simply add them together. Alright, so in this case the total uncertainty is simply the sum of the two of them. It is plus or minus 0.07 meters per second. Okay, and then our delta V is our 1.17 minus 0.41, which comes out at 0.76, which we can probably guess because that's most of our answers. So our answer should be 0.76 plus or minus 0.07, remembering that we keep those numbers of sig figs consistent. So our answer should have been B. Now we're back to combining using multiplication or division. So here we are using the formula wave speed is frequency times wavelength. Alright, so if we start by actually calculating our value for wave speed, that is our frequency of 70 Hertz multiplied by our wavelength, which is 43.5 centimeters. So make sure we convert that before we actually do the calculation, giving us a value for 30.45 meters per second. Okay, come back to that later. So once again now, because we are multiplying or dividing to get to our answer for V, we have to now work out the individual percentage uncertainties. So the percentage uncertainty in F is our absolute divided by our value times by 100, which gives us a percentage uncertainty of 7.14%. Our percentage uncertainty in lambda, we do exactly the same way, so 0.5 divided by 43.5. Again, remember I can leave them both in centimetres because it's relative. Times it by 100 gives us a percentage uncertainty of 1.149%, and therefore our total percentage uncertainty is the sum of those two, which is 8.289%. So our last step then is to work out the value for that absolute. So to do that, we take our value for V, 30.45 meters per second, and we work out 8.289% of it, and that gives us a value of 2.52. So we've got 30.45 plus or minus 2.52. Okay, and remembering that we need to keep our numbers of sig figs significant. So if we look at our options, 2.52 will round up quite nicely, meaning that our answer will be C, 30 plus or minus 3 meters per second. And then our last one, where we're looking for a value for volume. So here we are multiplying three quantities together. Okay, so we use exactly the same principles we've done so far. We calculate the individual percentage uncertainties and then we sum them. Okay, so all we're asked for here though is the total percentage uncertainty. So we don't actually have to calculate a value for V here. So if we just set apart finding the percentage uncertainty in each of them. So we start with W. Times by 100, and the percentage uncertainty in W comes out at 1.01%. Do the same for H. And H comes out at 1%, and we do exactly the same for L. 14.8, 0.675%. And then when you sum the three of those together, you get 2.6857%. And when we look at the values that we've got there, the closest one to those is that bottom one, D, plus or minus 2.7%. So hopefully that has taken you through three different types of examples. Okay, so we had level 1 where we were looking at calculating the absolutes either based on the precision of our equipment or taking repeat readings. We had level 2 where we were then making those uncertainties percentages, so working out their relative size in comparison to the actual answers, which hopefully was fairly straightforward. And then we had level 3 where we looked at combining them both when we had to add and subtract quantities of the same unit and when we had to multiply or divide them to get other quantities. Okay, so if any of this you are still unsure of, please just go back through the video and watch the relevant examples, because it's really important that you are confident in doing